logarithmic differentiation is an advanced rule that allows us to solve some of the most complicated derivative problems. If y is equal to a times b divided by c times d, where a, b, c, and d are understood to be functions of x, then we can take the natural log on both sides, and from our log rules, we would have the natural log of a times b minus the natural log of c times d. And this will be the natural log of a plus the natural log of b minus the natural log of c minus the natural log of d. Notice here we have quotient and product rules for the logarithm. Now if we take the derivative on both sides, so we'll differentiate on this side with respect to x and on this side with respect to x, we can again use our derivative rules and implicit differentiation. So notice here for this function, the derivative is not 1 over u prime, it's 1 over y prime, right? And this term is what we want. That's the derivative dy dx that we're looking for. All these terms, if they're functions of x, we basically have a prime over a plus b prime over b minus c prime over c minus d prime over d. Then we have our y prime is equal to y times this whole term, a prime over a plus b prime over b minus c prime over c minus d prime over d. Now you're probably thinking, oh, this is very complicated, I don't understand why you did all that. Let me show you with an example. Let's take what would be otherwise a terrible derivative to take using the product rule and the quotient rule and chain rule. Y is equal to x plus 2 times the square root of x squared plus x divided by x cubed plus x. Now if we were to find y prime by the usual rules of calculus that we learned earlier, we could take a quotient rule, and then when we take the derivative of the numerator, we have a product rule, and then we take the derivative of this term, we have a chain rule. Using this technique of logarithmic differentiation though, instead what we have is that the natural log of y is equal to the natural log of x plus 2 plus the natural log of the square root of x squared plus x minus the natural log of x cubed plus x. Then this is x squared plus x to the 1/2, so we can say this is the natural log of x plus 2 plus 1/2 the natural log of x squared plus x minus the natural log of x cubed plus x is equal to the natural log of y. Now we can take the derivative implicitly for this term, so this is 1 over y times y prime is equal to x plus 2 prime over x plus 2 plus 1/2 the derivative of this term, which is, let's say, x squared plus x prime divided by x squared plus x, and then here minus the derivative of this term, which is x cubed plus x prime divided by x cubed plus x. Now to finish this problem, we want to solve for this y prime right here, and we need to take these derivatives. So to do this, what we're going to say is y prime is equal to y times 1 over x plus 2 plus 1/2 times 2x plus 1 divided by x squared plus x minus 3x squared plus 1 for this term divided by x cubed plus x, close parentheses. Now for me this is okay, but if you want to match the answer in the book, you're probably going to need to replace this y right here with y right here. So to write the final answer, all in terms of x on the right hand side, our y prime would be equal to x plus 2 square root of x squared plus x divided by x cubed plus x, and then you have to multiply by all this. So 1 over x plus 2 plus 2x plus 1 divided by 2 times x squared plus x minus 3x squared plus 1 divided by x cubed plus x. So this, the final answer. It's complicated, but it would have been worse, I think, to try and do the product rule and quotient rule together. They're comparable, though, although you probably will be asked to solve a problem like this in class. In the final part of this video, let's try and understand where the formula natural log of x prime equals 1 over x comes from. So what's the idea of this formula? Well, the story of this formula starts with the exponential function. And the inverse of the exponential function is what we call the natural logarithm of x. Now, this was a question that was asked to nature, and the question is, find a function such that dy dx is equal to y. So there is only one function in all functions that satisfies this relationship, and it is this function, the exponential function, and we were able to discover it. The number e, Euler's number, and this exponential function was a consequence of asking nature this question and discovering the answer. Aliens come from another solar system and visit ours. They will have found the same function, and it will be the only function that can satisfy this relationship. Now, this one came from this function, but it's the inverse, and it satisfies the property that f of f inverse of x is equal to f inverse of f of x is equal to x, which in this case would be e to the natural log of x equals the natural log of e to the x is equal to x. Our derivation of this formula comes first from saying let y equal the natural log of x, and we want y prime to be 1 over x, but we don't know this formula a priori. So to find it, what we can do is exploit equality here. Since this is equal to this, they're identical. Remember, equals is the most powerful symbol in all of mathematics. If this is exactly the same as this, indistinguishable, then this implies e to the y must be equal to e to the ln of x. And then since the natural logarithm is the inverse of exponential function, this is equal to x. So this identity right here is a consequence of the definition. Then we can differentiate on both sides with respect to x. Implicitly, this one is e to the y times y prime, and this one is 1. Now we want to solve for y prime, so we do that by algebra. This implies that y prime is equal to 1 over e to the y. Notice that y is equal to the natural log of x, so this then is 1 over e to the natural log of x. E to the ln of x is equal to x, so this is 1 over x, and that is our proof. Quod erat demonstratum. So we have found a basic derivation of this formula. To briefly summarize this result, notice that we started with y is equal to the natural log of x. And then, when we got to this stage, y prime is equal to e to the y, we substituted y is the natural log of x here, and we substituted y is the natural log of x here. And then we again used this relationship to simplify this term to just x. So that was a property of inverse of this function.